Hello guys, this is Code and Code and this is 17th lecture of this graph theory series part 2. In this lecture we are going to introduce some of the algorithms which we'll be applying on grid. Now the question is, what is it all about? What is this lecture all about? So there are many problems which require application of algorithms like DFS, BFS or even Dijkstra's in some cases on 2D grid. And remember here 2D grid is not actually adjacency matrix representation of graph. No, it is not. Grid is completely different than adjacency matrix representation of graph. So do not be confused with that. So to solve these problems, which of course you have to apply these algorithms on 2D grid. Let's see what are some of the examples of problem which require BFS, DFS or even Dijkstra's on 2D grid, so that you actually know that learning these algorithms on the application of these algorithms on 2D grid is actually really important. So the first problem I'm going to talk about is jungle run from Hacker Earth. Now this problem can be solved using the application of DFS on 2D grid or even BFS. Now see, you are given n and you have given n cross n matrix. Each cell is either S, T, P or E. This is a jungle, so P represents path and T represents tree. You from each cell you can move either north, south, east or west. 4 direction you can move. Of course from here you cannot move upward direction, in the upward direction, because there is no cell available. So you have to start from S. There is exactly one S in the whole grid, and you have to end at E, and you cannot move from any valid cell to a tree. So you can move from here to here, but you cannot move from here to here because this cell contains tree. So you have to find the shortest path from start to end. So this is the problem all about, and this problem can be solved using DFS or BFS application of these two algorithms on this 2D grid. The next problem is from CSES, and the problem is counting rooms. Again, this problem can be solved using DFS as well as BFS. This problem was suggested by one of my followers, so I looked into this problem. This was quite interesting problem. Even though when we would learn application of DFS or BFS on 2D grid, you would see that this problem can be solved by the simplest implementation of DFS or BFS on 2D grid. This will be one of the simplest problem you will be able to solve using these algorithms on 2D grid. So the question is, these hash you are given n cross m matrix and each cell is either filled by hash or by a dot. Hash represents walls and these dots represent the floor. So you see, you have to count the total number of rooms in the whole structure. So you see, these two form a single room because these two are actually floor. So these two form a single room, these two dots form a single room, and this structure form a single room because all of these are separated by walls. So in total there are 3 rooms, and you have to print 3 because there are 3 rooms. After learning this algorithm BFS and DFS, you would see that this is nothing but counting connected component on 2D grid. That's all. And counting connected component on 2D grid using DFS or BFS is very easy. We'll see that in subsequent lectures. Now let's see some of the application of BFS on 2D grid. There is also a problem taken from Hacker Earth. I forget to mention the name of the problem. The problem is, you are given a 2D grid, of course, and of size n cross n. Each cell is filled with either 0, 1 or 2. 0 cell we have to do nothing about them, but all of the cells which are directly adjacent to any cell which is all of the cell which containing 1, which are containing 1, if they are adjacent to any cell which is containing 2, then in 1 unit of time all of those will be converted to 2. So basically all of the ones which are directly adjacent to a 2, for example this one is adjacent to this 2, these two ones are adjacent to this 2, and this one is adjacent to this 2. Similarly this and this are adjacent to this 2. So all of those which are directly adjacent to 2, all of those ones which are directly adjacent to 2 in 1 unit of time will be converted into 2. So this these all three, this one and this one, except this one, all of the ones will be converted to 2 in 1 unit of time. And after 1 unit of time, this is also 1, this is also 2, so this one is now adjacent to a 2. So in next moment this will be converted into 2 as well. So in 2 unit of time, all ones are converted into 2. So you are given a grid filled with 0, 1 or 2. You have to find the minimum time in which all of the ones will be converted to 2. This is the second problem, and this can be solved using BFS, using application of BFS. Let's move on for the next problem that can be solved using BFS, and this one is quite interesting. So basically you are given a knight on chess. You are given a chess and also a knight, and you are given 2 points. So there are 2 test cases. First point is this: first cell is A1 and you have to move to cell B1. So this is your source, this is the destination, and as we all know, the knight have 8 different moves. So starting from starting cell, you have to reach to terminating cell or final cell. So you have to start from 1A and you have to reach to B1. Sorry, you have to start from A1 and you have to reach to B1, and you have to count the minimum number of moves required for knight to reach to destination. So in the first test case, as we can see, we require 3 moves to reach from source to destination. Similarly, for second case, you have to start from cell G8 and you have to end at cell F6. This move can be performed in you can reach destination starting from source in only a single move. That is why we are printing 1. Now this problem can easily be solved using BFS on grid. Remember, whenever you have to find, most of the times when you are applying graph theory and you have to find the minimum number of moves, minimum number of steps and so on, usually either you will use BFS or die-cast. So this problem will be solved using BFS, and we'll see how we'll apply BFS to solve these kind of problems which look like complex but are really easy. These are simply applications of BFS on 2D grid, nothing more than that. The last problem I'll be talking about is chef and escaping from labyrinth. Labyrinth, or I hope I'm pronouncing it correctly. So this problem is taken from Code Chef, and I remember the time it was appeared in the live contest, I was not able to solve this problem. So the problem is you are given a grid of size n cross m, in this case 3 cross 4. Either the cell is 0 or some positive number or some negative number. So the cell which are filled with negative numbers, you cannot start from there. So that is why there are 3 negative cells. So you have to print B, B, B wherever there is negative cell, right? Now for the rest of the cell, you have to see whether you can reach any cell which is having positive whether you can reach starting from a given cell, say starting from this cell, this 1 cell, can you reach any cell which is having a positive value in less than equals to time which is having the value of that cell. So basically, starting from this cell, can you reach this cell in less than equals to 5 steps? So yes, you can reach, because when you start, you can reach here in 2 steps, 1 and 2. In 1 step you can go right, and then in another 1 step you can go right again. So allowed moves are up, down, left and right. So if you start from here, you can of course reach here in only 1 step. Here, starting from here, you can reach this cell. You have to reach a cell which is having a positive value, right? So starting from here, you can reach here in 2 steps. So yes for this, yes for this. And if you start from this cell, you are already in a cell which is having positive value, so no problem there. So that is why these 3 cells are having y, 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 which means yes. Starting from here, you can reach here in less than equals to 5 steps. Yes, 1, 2 and 3. In 3 steps you can reach there. Starting from here, you can reach this cell in 4 steps. Starting from here, you can reach this cell in 5 steps. So that is why this all of them are having yes. While starting from here, you cannot reach here in less than equals to 5, because you need 1, 2, 3, 4, 5, 6 steps. So you cannot reach from here to here in less than equals to 5 steps. That is why you will see no here, no here, no here, because starting from these 3 cells, you cannot reach any cell which is having positive value less than equals to the value of that positive integer. So that is why 1, 2, 3, these 3 cells, you cannot reach any such cell. That is why in the answer, these 3 cells are printed as no. So this is the problem that we will be solving, and this problem can be solved using Dijkstra's, or some people say you can solve this problem using BFS and priority queue, and I call that as Dijkstra algorithm. Maybe there is different, I do not know, maybe I do not have that much knowledge, but I believe this is Dijkstra's algorithm. So these are the problems that these are some of the examples that I'm showing you. There are many problems which require application of BFS, DFS or Dijkstra's on 2D grid. So we'll be learning how we'll be applying BFS, DFS or Dijkstra's on 2D grids in subsequent lectures. So this was all for this lecture. If you have any doubt or query, of course you can ask on the article that I've created for this course on discuss.codechef.com. So I'll be posting the link of that article in the description of this video. So this was all for this lecture. Thank you guys for watching. Until the next video drops, keep coding. Thank you.